Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I have a very ambitious plan for this lecture, and I'm not sure that we'll fit it all in. But this is some very serious meat. These are really powerful and useful techniques. Okay. Right. So the first technique that we're going to talk about is sometimes referred to as the sparse vector technique. And unlike everything else that I'm telling you about, it doesn't have a really clean, this is the paper in which it first appeared. Ideas came from several different papers. And so this is a child of very many parents. So we have a database of size n, and we want to answer a very large number of queries, but they're a special kind of query. This is going to be an online algorithm that will answer many queries. So far, the only thing that you've seen is an algorithm that took all of the queries at once and thought about them all as a whole and then produced a small synthetic database that answered all of them. Here, the algorithm has to work one by one. Now, these are going to be a little bit different than what you've seen before. We're going to have a set, as I said, of m queries that are presented online, but only k of them, for some much smaller k, are going to be called significant. So the queries in general are going to be sensitivity 1 queries, and a significant query is one where the value of the answer, the true answer, exceeds some fixed public threshold. So maybe the fixed public threshold is 258. So the first query comes along. It might be a counting query. It might be some other kind of sensitivity 1 query. The true answer is, what did I say our threshold was going to be? 258? So let's say that the true answer is 106. So the system doesn't say 106. It says below threshold. No answer. Then the next query comes along, and the true answer is 700. And it says, this one's significant. 700 is much bigger than the threshold. So here's an approximation to 700. It's going to add some noise. It'll be like 722. All right. Then the next question comes along. The answer is 3. It says insignificant, below threshold. Is it clear? So the only thing, most of the queries, the promise somehow is that most of the queries are going to be below threshold, and it won't be saying anything except below threshold, below threshold, below threshold. Oops, this one's above threshold. Here's the answer, approximately. Below, 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 below. Above, here's the answer. So the promise is that there are only going to be k significant ones, where k is something like the size of the database, n. And that's easily enforced. Because this statement of, yes, this one is significant, is made in public, everybody, both the database administrator and the data analyst, can count how many times that has happened. So everybody will just count up to k and then quit. So again, the goal of this algorithm is to sort of detect and release values for the significant queries. And the key here is that we are going to, in some sense, get the insignificant queries, of which there are a huge number, for free. In terms of our privacy price, we're only going to be paying for the significant ones. So I forgot my animation. All right. So the first 2 in this picture are significant, and then you get a whole bunch of insignificant ones, then you get a significant one, and then 2 insignificants, and so on. So here's our first try at an algorithm. When I'm given a query, which is a function, f sub t, I'm stressing for no particular reason that this is a general sensitivity 1 function. Think of it as a counting function, a counting query. So if the answer is below the threshold, it's insignificant, output, this is the symbol bottom, and it says this is insignificant. And otherwise, draw from the Laplace distribution and give the noisy answer. So the idea is that we're going to run for up to k significant queries. We'll choose the parameter to the Laplace to be k over epsilon so that we won't break privacy. And that's it. So does it work? What's wrong with this algorithm? Well, the first attempt says it's obvious, right? We only have k significant queries, so there are going to be at most k invocations of the Laplace mechanism, blah, blah, blah. But you have to be careful. This conditional branch is leaking some private information. There could be a pair of adjacent databases where on one database it's insignificant, but on the neighbor we would just have crossed the threshold and it would be significant. So the fact that I'm saying it's insignificant is leaking some information. And the whole name of the game is going to be to show that that doesn't actually leak that much information. First thing that we're going to do, so it's clear that because this leaks private information, we're going to have to add some kind of noise to it. Either we're going to add noise to this and compare it to the threshold, or we'll add noise to the threshold. That's the same thing because our noise is symmetric. It turns out we're going to do both. And you'll see exactly why in the proof we chose to do both. That will come. So the algorithm is going to take as input the database X, this threshold T, that's publicly known threshold, the number K of queries that it's just going to quit after k queries. I didn't put that into the structure of the algorithm, but we all know that's what's going to happen. And epsilon. So first thing that we do is we perturb the threshold. We choose a t hat, which is close to t, and we're going to blow half of our privacy budget there. Okay? And then we'll use the other half of the privacy budget for the rest of the proof, the rest of the algorithm. So on query fi, we compute a noisy version of the answer. So instead of scaling to k over epsilon, we're going to scale to 2k over epsilon because we only have an epsilon over 2 left in the privacy budget. And so if this noisy answer is less than our noisy threshold, then we'll output bottom, and otherwise we'll just output the noisy answer. So that should have said utility and accuracy. All right. So what are some of the things that can go wrong that we have to watch out for in terms of accuracy and utility? So one thing is we're only going to answer k significant queries. If when we chose the threshold t hat, we ended up choosing something ridiculously small, then everything might end up looking significant. Like maybe t hat is a negative number. Very negative number. It's extremely unlikely, but maybe that happens. And then everything seems significant and we don't get any utility out of that. So that's going to end up, of course, being kind of very unlikely by the properties of the Laplace distribution. Another thing, of course, that could happen is we could choose the threshold t hat to be very, very much too big, and then nothing would show up as significant. And that's not interesting. It's not a good algorithm. And of course, that's not a problem either. And in general, we're going to try to prove some kind of an alpha utility. So what we really want is that we're not very likely to be very far from the true threshold. And that's, we know that that's going to be sort of exponentially unlikely in the degree of farness. Okay? The other place that things can go wrong is that let's assume that we were really lucky and t hat is relatively close to t, and we're never going to worry about that again. I mean, we've taken care of that with our sort of probabilistic argument. All right, so now what can happen is when I add noise over here, something weird happens. So I could get an artificially too large answer. So here, f of x is less than t hat and less than t, but my Laplace noise took it over the threshold. So there's some possibility of that, but again, that's going to be exponentially unlikely in that length. We could just get a weird answer. So it's truly over threshold. It's very far over threshold. It's extremely far over threshold. And when we add random noise to it, we get something that stays over threshold, but it has nothing to do with the actual value because we had a very unlucky choice from the Laplace here. So f of x is in fact way above the threshold, but I get a very bad answer because I had an unlucky noise. That's another thing that can happen. This has got to be the same kind of thing. It's really above threshold. I added big negative Laplace noise to it, so it shows up as being below threshold, and we missed it. Again, unlikely. So remember that argument that we used for alpha beta accuracy 1 or 2 days ago? We made an argument about alpha beta accuracy of the Laplace mechanism. It's exactly the same argument that we use here, so we're not going to really go over it in detail. We know that with the definition of alpha beta accuracy is somehow that with probability at least 1 minus beta, all of our answers are within alpha of reality. And so what do we want here? We want to say, first of all, if we say at step I that the query is significant, then the value that we report, we want to be within alpha of the true value. Because we're reporting a real number, and we want this to be a relatively accurate real number, not weird noise effects. We also want that if the true value, well, maybe if it's not actually less than the threshold, but if it's, we'll give a little bit of slop there. Maybe it's over the threshold, but only by alpha. But if the true value is less than t plus alpha, then we certainly want to say that it's insignificant. Sorry, so if it's less than t, we want to say that it's significant. We'll relax it a little bit and say if it's within t plus alpha, we'll say it's insignificant. No, I'm saying this wrong. I'm saying this wrong. I apologize. If it's insignificant, if it is reported as insignificant, then it shouldn't be much above the threshold. That's what we want, and that's what that says. If it's insignificant, then it isn't much above the threshold. Now, we also want, am I making any sense here? No, I'm sorry. What I wanted to say is, well, you're right. The second line is correct. What I want to say is, if it is reported as insignificant, no. If this happens, then that happens. If it's far below threshold, then we want to report it as insignificant. Sorry about that. All right. So it's sufficient to get all these, the conditions when they're correctly written, that with probability at least 1 minus beta, the maximum error that we got in this Laplace plus the error that we got when we're choosing the noisy threshold will be below alpha. So in our analysis, we'll allow an alpha over 2 error here and an alpha over 2 error here, and then the sums of the errors will be at most alpha. And that will follow in the usual way. So the probability that the max error when I choose from either one of these guys will be bigger than alpha over 2 is at most by the union bound and the properties of the Laplace distribution, which you saw already in the previous discussion of alpha beta utility. It's m for the total number of samples here, and then e to the minus alpha over 2 sigma by that property in the top, the properties of the exponential decay of the Laplace noise. And similar argument, of course, for this guy. His troubles are very small compared to his troubles, so I didn't bother drawing them. So what we get then is, just by manipulating that top line, if we take sigma to be 2k over epsilon, we end up with this bound on alpha. Okay? So that is, roughly speaking, the kind of accuracy that we're going to be able to guarantee. And the interesting question now will be the privacy analysis. So the algorithm runs. At each step, it gives a response. The response might say insignificant or bottom, or it might be a real number. So I'm going to call the responses that we get in round I R sub I. So we get a sequence of responses, the response for round 1, the response for round 2, round 3, and so on. And just the letter R is going to be the name for this sequence. So the sequence of responses is a random variable. And we want to bound the ratio of the probability of seeing any sequence of responses when the database is X over the probability of seeing that same sequence when the database is the neighboring X prime. That's the usual thing we need to bound. And that's going to just be the product of the probabilities. So we're getting a sum of the logs of these ratios, where this notation means the probability that in the round I, we end up seeing little r sub I, conditioned on everything that happened in the previous I minus 1 rounds and the fact that the database is X. And here we're conditioning on the same thing, but the database is X prime. And we want to show that this is bounded by epsilon. So this is the quantity that we need to investigate. Yes, should I go back?
How can array equals to small array?
Sorry?
How can capital array equals to small array? You say that it can depend on the previous inputs.
So capital Ri is the response that we get in round I,
Yeah.
conditioned on everything that happened in the past.
I mean, does it really depend on the whatever happened in the previous inputs? Because just choosing them.
There is some kind of, you're right that there are independent noises being chosen, but there is some kind of connection because, say, the threshold was fixed once at the very beginning, and these guys may all be related to each other because of that threshold. Okay.
So the dependence is caused by the fact that t hat is the same.
Yes. Yes. So that Ravi is stating more cleanly what I just said, that the dependence might be caused by the fact that t hat is fixed the same for all of them. So we're just going to condition on that. All right. So I'm going to take this sum and I'm going to split it into two parts. One part is the contributions from the significant rounds, and the other part is the contribution from the insignificant rounds. The insignificant rounds, of course, are going to be the really interesting ones because there are lots and lots of them. We already know that we scaled sigma to handle, in some sense, what's going on in the rounds that are significant. So let's just check that. If the round I is significant, then a real valued output is produced. And we have the noise value that's generated in that round. So that's this draw from the Laplace distribution. So the contribution that we're getting to this sum is the log of the probability that the noise is equal to Ri, this actual response that was produced, minus Fi of x, versus the probability that it's Ri minus Fi of x prime. And since these two numbers can differ only by 1, we get the epsilon over 2k from the fact that sigma is scaled to 2k over epsilon. So that's the usual thing. So just add them all up. There are at most k such events, the total privacy loss is epsilon over 2. That's not the interesting case. That's the stuff you already know how to deal with. Now we're going to start with the interesting case. So this is where we're going to use the fact that we randomized the threshold. In here, we never used the fact that we randomized the threshold. So it has to come up now, because this is the end of the argument. I mean, these are the only two cases. If we didn't use it in the first case, we've got to use it here. OK, so fix some x and x prime, and fix the draw from the Laplace distribution. Fix the value of t hat. And because this is an insignificant round when the database is x, we have that f of x plus this noise is at most z. We fixed the noisy threshold at z. It's insignificant, so it wasn't reported as above threshold, so it's below threshold. OK, so let's look at f of x prime. Clearly, if f of x prime is less than f of x, we're going to also have f of x prime being less than z. That's obvious. But what if f of x prime is bigger than f of x? Well, we can't say that we're going to end up with f of x prime being less than z, but we can show that it's going to be less than z plus 1. OK? So why is that? Well, we have that, I mean, it's just obvious. The sensitivity is 1. So formally, I added this in on both sides. So this and this are going to cancel. And over here, it's at most 1. So we get that. So if f of x plus this noise value is less than z, then f of x prime plus the noise value will be less than z plus 1. Simple. So now, how do we use this? We're going to introduce a piece of notation. These are the insignificant when the threshold is z and the input is x, I sub z of x. So it's going to be the set of the values of the noise variables from our draws from the Laplace mechanisms, which lead to insignificant for every I in the set of rounds where we got insignificant on x, conditioned on t hat being equal to z, and all of the responses that we got for the significant ones. So we have this output here. Some of these guys gave us some actual values. So I'll use A to mean a value, a real number. A1, A2, bottom, A3, A4, bottom, 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 and so on. So I'm fixing all of the locations here and here. And I'm fixing these values, and I'm fixing the threshold, and I'm looking at what are the values that could give, conditioned on all of those things, what are the values that could give bottom here when the database is x. All right? And the claim is that if a noise value could give insignificant here when the database is x and the threshold is z, then that same noise value will give insignificant here when the database is x prime and the threshold is z plus 1. That's because, that's exactly a corollary of this. It's exactly what we're saying. And this is true whatever x prime is, the adjacent database. So That's what the claim says. This is just what we said, and the proof is that line. All right. So again, this says that a noise value that leads to bottom on x when the threshold is z also leads to bottom on x prime when the threshold is z plus 1, and therefore the sequences of noise values that lead to insignificant on x when the threshold is z will all lead to insignificant on x prime when the threshold is z plus 1. That's what we need for the rest of the proof. So let's go. I want to show that the product, I want to look at this product. So what is that? Well, I haven't conditioned on z here, so I'm going to integrate over all choices of z of the probability that that's what we got for our noisy threshold times the probability that these particular, that the draws from the Laplace mechanism will give us insignificant when the threshold is z and the database is x. Okay, so that's exactly that. All right, well, this is going to be at most e to the epsilon over 2 times exactly the same stuff conditioned on t hat being z plus 1. Because the probability of t hat being z plus 1 is at most e to the epsilon over 2 times the probability of t hat being z. Okay. Now, this set is contained in that set. So this whole quantity is at most this whole quantity. This guy maybe a little bit more. So this is bigger than that because there are more choices over here. Possibly more choices. Maybe it's the same, but possibly more choices over here. Great. But, when everything else is fixed, if a given value gets me over the limit when the threshold is z plus 1, if I drop that value and the threshold by 1, it'll still get me over the limit. I have a higher threshold and a bigger noise, it gets me over. If I subtract 1 from the noise and 1 from the threshold, it still gets me over. So that's what's going on here. We were able to replace this z plus 1 and this z plus 1 by z and z. All right? But look at the form of this. It's exactly the form of what we started out with here, only instead of having an x, we have an x prime. So this is exactly that. Yes?
What is small t?
What is what?
Small t.
That small t was the number of locations that were insignificant with z and the history so far and x. So these are all of the ones that we have to look at.
So the small t is less than I.
It's the size of I. It's the size of I. Right. Okay, is that clear?
So look at one insignificant value, right?
Yes.
There is a certain answer. Call that answer A.
No, don't call it an answer because answers are these actual real values that are released to the public only when significant things happen.
So the true answer.
Okay.
Let's say it's A, right?
All right.
Wouldn't you only get into trouble if the threshold is A or within one of them? Yeah.
Yes, that's the only time you're going to get into
One of it.
Yes.
And the probability of that should be at most epsilon over 2.
Right.
But that's for one query.
That's for one query. And the point is, by randomizing the threshold, we're finding a way to take all of these reports of insignificance and bundle them together.
What if I just repeat that one query ad infinitum?
You would have a little bit of a privacy loss each time. Here, we're capturing everything by this change. And we're only paying once. Okay? Yes, the integral is minus infinity to infinity. Yes. Anything else? Okay. So, just to summarize what we just showed, we have a database of size n. We have a very large number of queries altogether. We're going to be able to handle k significant ones, and the algorithm will just turn itself off after handling k significant ones, and it won't be a surprise to the analyst that the algorithm is turning itself off, because the analyst also can count to k. So there's no information leaked by the algorithm saying, I'm done, I'm not answering any more questions, right? The queries are sensitivity 1, blah, blah, blah. And the goal was to find and release values for the significant queries while paying only for the significant ones. The theorem that we end up with is that it is epsilon 0 differentially private, and it's alpha beta accurate for this value of alpha, which again, we briefly went over here and we went over in detail, I think, 2 lectures ago. Good. Now, how could we do better? How could we get more accuracy? I want to do even better. Sorry? Exactly. I want to somehow get root k instead. Why would I might be able to do this? From the composition theorem. But I have to have something to compose. Here I have an algorithm that's standing all by itself. So let's modify this algorithm very, very slightly. Oh, sorry about that. Yeah, let's get to the point. Let's modify it very slightly. The modification is the new algorithm is only going to run until it gives its first significant answer. And then it quits. Now, why is this progress? Well, let's just compose it with itself k times. Now we have some nice composable object. It's epsilon 0 differentially private. We'll compose it. We'll run it k times. And that's the answer. That's the algorithm. It gets repeated k times. So we'll have to choose. So this is, before this had been scaled to 2k over epsilon. Now I'm only answering 1, so this becomes 2 over epsilon. But I'm going to take this whole thing and I'm going to compose it with itself k times. So I'll need to choose a different value, epsilon prime, that's suitably smaller than the epsilon that I want as my overall goal. Let me see. Did I tell you? Yeah, I told that on the previous slide. So what is that suitable value? Well, 8 divided by, so epsilon divided by square root of 8k ln 1 over delta. And then I'll get epsilon delta privacy. The accuracy argument just changes a tiny bit because we have many randomizations now of the first threshold, so we have to be sure to take care of that in our proof. Nothing interesting is happening, I swear to you. It's just a detail when you want to say that you've proved this thing. You have to watch out for that. Okay, so that is the sparse vector technique. Again, it showed up implicitly in many different ways. And then, yeah, all right. Yes?
If this is true, then a strong analysis could have told that even the previous algorithm had the same bounds. So it's essentially the same algorithm, right?
Do you want to answer, or you haven't answered?
Well, it's not the same. Because the threshold is reset after every significant. And also the noise you're getting is 2 by epsilon over here, that is, where it was 2k by epsilon.
Well, but we'll use, yeah, right, that's true. So the difference has to do with re-randomizing the threshold after each significant query.
Every time this algorithm was called, every time a query was asked, wasn't a new noise sampled from Nakash 2 by epsilon? And
Yes, new noise was sampled here, but not here. And we need that. We need that for our privacy proof. My ability to collect all of those events, all those insignificant events together and tie them to the choice of T hat is really important. And when I compose, I have to be able to do that multiple times. Let's talk after, because I think I'm not giving you an answer that's satisfying you, and maybe we can make that more clear later. Okay. Remember the medical cohort application, cohort that I mentioned yesterday for looking at concentrated differential privacy? So according to my expert, who is the Lucila Ono Machado, who is the director of a National Center for Biomedical Research at UCSD, what really happens when you want to form a cohort is you have in mind some ideal set of patients, and you say, I want patients whose blood pressures are in this range and whose weight are in this range and this fraction are male and so on and so forth. And she says what happens, and I'm just reporting what she tells me, is that typically they don't get exactly that. There aren't quite enough people of that type. So the researchers relax their requirements and say, well, how about now with these relaxed requirements? And so on and so forth, until they finally get a relaxation which they feel they can work with still, and the database has enough people. So this is a little bit like what we're doing with sparse vector, right? The analyst says, how many people in the database satisfy this property? Or are there enough? And the analyst says, the database says, no, actually there aren't enough. So they relax their condition, and they ask again, are there enough? No, there aren't enough, and so on. But after a number of queries, the answer is yes, we're above threshold. So significant queries are more rare than the insignificant ones. So it's conceivable that we could apply it in this context, but notice the question mark. I don't know for sure. I don't know whether the numbers are good enough. That actually reminds me that there was something I meant to say yesterday, and I didn't say. I hinted toward the end of the talk about an idea of this kind of concentrated notion of differential privacy, where we relax the requirement a bit, and we say, well, the probability of having a privacy loss of k epsilon is, let's say, exponentially small in k squared. All right. What I should have told you also is that this behaves under composition exactly the same way that epsilon 0 and epsilon delta behave. That is, if you look at the cumulative privacy loss that an individual suffers over many mechanisms, each of which is concentrated differential privacy, you get the same kind of behavior of the cumulative loss, the same bounds on the cumulative loss as you would have had all of them been epsilon 0 or epsilon delta differentially private. So your cumulative loss isn't any worse. Okay. Next algorithm. This, as it's going to be presented, is an application of the sparse vector technique. The theorem is that you can answer a whole lot of, let's say, counting queries, or slightly more generally, linear queries online, just like we did with sparse vector. And the errors that you get look like the square root of n, the square root of the total number of queries, the fourth root of the universe size, and the log of 1 over delta. Yeah, I think that's right. Okay. Now, remember I mentioned 2 lectures back, 1 or 2 lectures back, that it's sometimes useful to represent the database instead of being a bunch of rows, each row belonging to one person, as instead a histogram over the universe of all possible databases, all possible people. So that histogram representation, again, is a bunch of counts. We have a universe of possible people. Let's say if people are represented by k attributes, this universe has size 2 to the k. And we have some number of people of type 1. All their attributes are 0, let's say. We have some number of people of type 2, some number of type 3, and so on, up to some number of type u. Okay? So we're going to be using that. We're going to think about this vector, this database as a vector like this. Except for one more thing, we're going to normalize it. So I'm going to take these numbers, these counts, and I'm going to divide them by n. So now this is like a probability distribution. They sum to 1. So I'm going to represent the database as a probability distribution over elements in the universe. Okay. So forgetting about privacy for a minute, multiplicative weights algorithm is going to would give us a way of interacting with something that is accurately answering queries, because we're forgetting about privacy for a second. So the queries are going to come in. We can think of the queries as being vectors where the coefficients in each vector are just between 0 and 1. Okay? So if you were asking how many people in the database have property P, you could look at each of these different types of people, say which of those evaluate to 1, make the query 1 in those positions and 0 everywhere else, and then take the inner product with the database. So this is how we're thinking of our queries, and because we're not worrying about privacy, the response is just this inner product. Okay? And what we would do is the algorithm will maintain some public estimated histogram, xt, which initially will be the uniform distribution, just 1 over, I lied to you. I said divide by n, divide by m, the size of the universe. So it's just going to be 1 over the universe size in every location. That's this initial, I don't know anything histogram. And we're going to update this based on the responses. So for example, if the response, the true answer of ft inner product xt, sorry, if ft inner product with the true database x is smaller than what we get when we apply xt to the estimate, the currently existing estimate, which starts off as the uniform distribution, so xt is yielding too large an answer, then what we're going to do intuitively is decrease the weight of each element in the histogram where ft of I is large. So because I is kind of leading in the wrong direction. And we'll increase the weight for each I where ft of I is small because it's leading in the right direction. Now, so that is how the real live non-private multiplicative weights algorithm would work. We want to make a private version of it. And I'll talk a bit about why it works after we present the private version. Private multiplicative weights. We're going to have a threshold t, bound sigma, and some eta less than 1. There is going to be an input histogram, just as we've been describing. And the algorithm will maintain a histogram x sub t, which is kind of its approximation to the real database. And it's going to start off as uniform because initially, because that's what happens in the multiplicative weights. Now, the algorithm's going to maintain this, but so will the data analyst. X sub t will never be a secret. X is the secret, but x sub t will never be a secret. So when things happen, based on the outputs of the algorithm, both the algorithm and the data analyst can update that histogram. Or if you like, the algorithm can keep xt in some visible public place, and it just does the updates there. Okay. So here's the algorithm. When you're given a query, ft, you compute a noisy version. We'll call that ft hat of x. All right? And we'll check. Is it far away from the threshold? I'm sorry. Is this guy the estimate that anybody could do using the publicly available x sub t minus 1? Is it close to this approximation to truth? Right? ft of x is the truth. It's an approximation because we're adding some Laplace noise. And so the algorithm is checking to see whether this publicly computable estimate is close to the approximation. Where close to is within some threshold t hat. Right? Why is it t hat? Well, it's going to be because of the same reason we had to randomize our threshold in the past. This is some threshold t plus some noise. If so, this is not a significant query. What the mechanism is saying is, you already have enough information to compute a good approximation to this. You've got it in xt minus 1. That's the significance, that's the semantics of the phrase insignificant. The existing approximation, xt minus 1, is good enough. So you just set xt to xt minus 1, and you take that to be the answer to the query. On the other hand, maybe our approximation to reality is very different from what's computable from the public information, the public estimate. This becomes a significant query. So you output this approximation to the truth. And then comes the updating of the publicly visible estimate of the publicly visible distribution. This thing that started out uniform and is getting updated. Here is the form of it, which just is really confusing, so let me walk you through it. First of all, okay, what are we doing? We take whatever we had before in this position, and we're going to multiply it by e to the something. This eta is a parameter. It's less than 1. All right. And then there's this quantity, st of I. And I have to tell you what st of I is. And there's the form of it, but as I said, I find it very confusing. The first thing is to notice that because this value is between 0 and 1, so is 1 minus that value. Okay, so this guy is never going to be negative. I'm not sure why I thought that was so important to tell you, but it's true. So you're going to do these updatings, and you're going to renormalize. So what's going on here? In this case,
you need it to be non-negative because otherwise you will round it to 0, and then that's a different answer.
Otherwise, you will round it to 0.
STs are frequencies. No, sorry, STs are non-negative.
Well, I'm just pointing that out, but I don't understand, for example, why you couldn't have raised the weights of some and lowered the weights of others and then normalized it. So there is a pointer in one of these slides to your fabulous survey. And we should all read it. I've read it, but I'm still studying it. But if you, do you want to say more about this? Okay. All right. So suppose what this condition says, this approximation to truth that the algorithm computed is smaller than what the estimate gives you. Right? That's exactly what this says. The estimate is bigger than the approximation to truth. So in that case, since everybody's weights are sort of getting lowered and then things get renormalized, lower weights, we're going to lower the weights on the larger ft of I more than we lower them on the smaller ft of I. Because we're going to be lowering them by ft of I. So if it's bigger, we're lowering it more. If it's smaller, we're lowering it less. Now, if, on the other hand, the estimate is small, then we're going to flip it around. And so we will lower the weights on the smaller ft of i's more than the weights of the larger ones. So the updatings are going in the right direction. And then we renormalize. Okay, so that's the algorithm. Why is it private? I maintain that I don't have to tell you anything I haven't already told you about why this is private, that you know the answer. Almost. There's one more thing I would need to tell you. Let's assume that I have very few significant queries. Why is it private? Have you seen something like this before? I have a bunch of queries. Most of them are insignificant, and I say, ugh, I don't have anything interesting to tell you that you don't already know. You could call that bottom. And for the rest of them, I tell you the approximate answer. Where did you see that? It's the sparse vector algorithm. It's exactly the sparse vector algorithm. And as long as I can argue to you that there aren't very many significant queries, this is going to be both useful and private. So first of all, we can, of course, impose the condition that there aren't going to be many significant queries by monitoring and turning off after some number k of queries, just as we did with sparse vector. And so the only interesting question that remains is, why is it that if I answer some relatively small number of, if I have relatively small number of significant queries, I'm still actually able to give you answers, or you can compute answers to lots and lots of queries. So the theorem is that if U is the universe, and remember eta was one of these, it was the parameter to the algorithm. Here was eta over here, and here it shows up in the algorithm. So it says that there are going to be at most the log of U divided by eta squared updates. There are only going to be that many significant queries. And that's really, really, really amazing. Well, yes. The answer is yes. Now, the answer is yes. There is some incredibly painful setting of the parameters that will end up showing you that you really can't get decent accuracy once the number of queries gets above, I don't know, it's like 2 to the n to the 1/6 or something like that. So in fact, there's a natural stopping point that otherwise utility goes away. And I'm not going to do that incredibly painful setting of the parameters. It still hurts me every time I look at it. So your question is good, and there's this accuracy, whatever, trade-off because of the privacy conditions that we have to. The de Noor-Niessing thing said you can't answer 2 to the n queries with accuracy little o of n, right? So we know we have to stop before we get to 2 to the n very accurate answers. So, okay. Now, I said this is an amazing fact. It also has essentially nothing to do with the fact that this is private multiplicative weights. This is just a property of the multiplicative weights update algorithm. All right? And I'm actually going to refer you to this survey that I alluded to, which is just mind-blowingly beautiful by Aurora, Hazan, and Kale. But the strategy for this proof. Sorry?
It's a topic that's beautiful.
The topic is beautiful, but the survey does it justice. It really was very, very helpful to me. So the technique that's used is a so-called potential function argument. Remember this KL divergence that we talked about. So at step T, do you know what a potential function is? Have you seen potential functions? So many of you have not.
But they've seen them in the physical. Potential energy.
Okay. Do you want to say more?
Maybe you're getting the high school, like gravitational potential energy, right?
Right.
So you work against the field and you get potential.
That's true.
So they've seen it in that context.
Have you seen it in that context? Oh, okay. This is great. All right. So our potential function, we're going to have this function that we compute more or less. I mean, the user won't get to know this thing. The algorithm could know it, but it's really a tool that's just used for the analysis. It doesn't show up anywhere in the algorithm. Remember, xt is kind of the approximation to x that's known at time t. That's right. We started with x0, which was just uniform, and we updated it after round 1, round 2, round 3, and so on. So the definition of the potential function, the value of the potential function at round t, is the KL divergence, which we already went over in a previous lecture. There should be a second line here of x with xt. And that's just the sum of xi ln xi over xt of I. Okay? Now, this is always greater than 0, as we discussed before from the log sum inequality. So we have this quantity, and it's going to start at some value, which you can convince yourself easily will be at most the log of the universe size. And the argument is going to show that this value will drop by at least eta squared at each update. I'm bothered by whether this is eta squared or 1 over eta squared. No, eta squared at each update, okay? The argument technically actually shows this, that at update t, at update t, it's going to drop by at least eta times the inner product of st and the difference between the estimate and the truth, minus eta squared. And again, that argument is not special to the fact that this is private multiplicative weights. This argument shows up in many kinds of multiplicative weights algorithms. And you can see this argument both in the private multiplicative weights paper, but also in the survey and the papers that the survey draws on. Okay. So then, when you combine the alpha beta correctness of sparse vectors and the parameter choices for t and sigma, you end up being able to argue that with high probability, updates are only triggered when this quantity, the error, the true error between the publicly available estimate and the truth is at least t over 2. And okay, then you take the definition of st and you plug that in here, and you do more parameter, and you end up showing that this is going to be at least eta times t over 2 minus eta squared. So in other words, we plug this t over 2 in over there. And then you do some more parameter choices to arrive at eta squared. So as you can see, I'm really allergic to the parameter choices subtleties. But the structure is just the structure of the usual multiplicative weights algorithms with just a little bit of extra effort because of the privacy. But you have actually seen that extra effort. That's exactly what happens in the proof of alpha beta utility for sparse vectors, for example. Yes?
Mr. Duncan, should this capital B be chosen appropriately?
Yes. That's part of the painful parameter choices of T and of sigma. Yes. And I'm not going there. Okay. See, there are these various parameters, and they're all interrelated in a tight way. And I have not found a simple way to really understand it, and therefore I can't have a simple way of explaining it. Okay, so let's look at some of what we've seen. We already talked about using the exponential mechanism or report noisy max to get an offline algorithm for counting queries. You saw that like in lecture 2, I think. There is a paper which we will discuss next. Oh, let's go here first. This is the online case for counting queries. That's just what we talked about. The next thing we'll do is we'll get less specific. Do we have time? Yes. Yeah. We'll become less specific, and we'll go to arbitrary low sensitivity queries. The linearity of the queries played an important role in this argument. It shows up here somewhere. And we don't have linearity anymore. So I'll show you next an offline algorithm that handles arbitrary low sensitivity queries. And then there is also an online algorithm for arbitrary low sensitivity queries, which in some sense falls out of a lot of the techniques that you have heard of, plus maybe one more. And the only place I know of to find that right now is Aaron Roth's online course notes. Okay, so we're going to use another power tool from learning. And this power tool is called boosting. So what is boosting? At a really high level, it's a general method for improving the accuracy of any given learning algorithm. So for example, this is the example that you always see in the literature. Suppose you have some algorithm that can look at email messages and does a pretty good job of classifying whether they're spam or not. It doesn't do a perfect job, but it does a pretty good job. So then what the algorithm does is it says, let's take this heuristic that does a pretty good job at recognizing spam. And let's kind of use it to handle some examples, kind of forget about those a little bit, and look at the remaining guys, the remaining examples that are spam that the first guy failed to do, grab some of those, run the heuristic again, or you run a different heuristic with those guys that handles a little bit more. Now run a different heuristic with the remaining guys, handles a little bit more, and let's put them all together. So roughly speaking, it takes a base learner that can receive labeled examples and outputs a heuristic that is pretty good on the distribution that you gave it. And then you run this many times and you combine the resulting heuristics. So procedurally, it looks kind of like this. We have a distribution on some set that we're working with, might be email messages. We feed examples from this distribution, labeled examples. This is spam, this isn't spam, so on, to a base learner. The base learner is going to output a heuristic. This heuristic is going to have the property that it will do well on just some constant more than half of a fraction of the weight of the distribution. Based on that, we're going to, what? Right. Okay, so you feed this to the base learner, it gives you a heuristic. Maybe if this is the teeth round, you've been collecting the heuristic from the first round, the second round, the third round, and so on. You have some way of combining them. If the combination is good enough, you say, okay, we can quit. And otherwise, if you can't quit, you're going to update your distribution on, say, email messages. You're going to take the email messages that are poorly handled by your combined thing or by A, you're going to boost their probability. So you're going to change the distribution by boosting the probability of the unhappy samples. And then you'll start all over again with this new distribution. You're going to feed it to the base learner. Now when you sample that, you're going to get more of the unhappy guys, the guys that weren't handled well by the previous one. Feed it to the base learner, it's going to do well on this new distribution, and so on. So that's the shape of these things. The base learner, it doesn't always have to be this way, but for what we're going to be doing, the base learner is only going to see samples, not all of the distribution. That's going to be important for our particular privacy proof too, but it's true that a lot of the things in the literature, even before privacy, has this. And the only interesting things that we have to do now in order to say what is a particular boosting algorithm is say, how do you combine the heuristics? How do you determine whether to terminate or not? And what is your update method? Once you've specified those three things, you have specified your particular boosting algorithm. So again, boosting is a general framework. It can work with samples. And in order to specify the particular boosting algorithm, you just need to say, how do you combine the heuristics? How do you check whether it's time to terminate? And how do you update? I'm going to show you an example, just so that it's less abstract, but I'm not going to go into detail. We can go back into the analysis later if it's interesting. It is multiplicative weights. Yes. Please bear with me. And ask it again when I get to the slide after this one. All right? So just to give you an example, you have some initial distribution. It's uniform. S will always be a subset of K elements. Just for concreteness, the combiner could be the majority. So you have something that classifies yes or no. You produce one of those at each round. The way you combine is you look and say, what do the majority of the heuristics say? If the majority says spam, then it's spam. Then we'll call it spam. And if the majority says it isn't, then we say that it isn't. Or you could do the median or something like that. Okay. Weight update. If the thing is correctly, yes? That's what we feed to the base learner. We choose a set of samples from the distribution. We call that set S. We feed that to the base learner.
And K elements drawn from D, right? It's not.
You're right. Well, each one is drawn from D, so it's a product distribution, and that's why I wrote D to the K. Right, but each one is drawn from D independently. Okay, so the weight update might be that if this thing is correctly classified by the current heuristic, let's decrease its weight. If it's incorrectly classified by the current, decrease its weight by a factor of E, which I'm going to call as subtract 1 from the exponent. So I'm going to have an E to the something. When I decrease the weight, I'm just going to subtract 1 from the exponent. If it's incorrectly classified, then I need to boost its probability so that it's more likely to get fed to the base learner next time round, and something may be produced that is more likely to make it happy. So if it's incorrectly classified, I'll increase the weight by a factor of e, which I'm calling adding 1 to the exponent. Then we renormalize. So that's an example of how boosting can work. Now, we're going to do something really different. We're going to be applying this to queries. The private multiplicative weights algorithm that you saw before was boosting people, changing the weights of universe elements. We are going to be changing weights on queries, okay? So it is very different, and it has very different privacy consequences, which we will see. So our goal is the following. Given a database, which I guess I'm calling DB, and a set queue of low sensitivity queries. They don't have to be counting queries. I want to produce some kind of an object. Maybe it's a synthetic database, but maybe not. Maybe it's some kind of generalized data structure. That's why I'm just calling it an object. So that the data analyst, when given this object, can, for every query in Q, produce a good approximation to the value of Q on the database. That's my goal, to produce some kind of an object that allows good approximations to Q of the database. For now, for the boosting algorithm, we're simply going to assume the existence of a private base learner that, given an object O, will give good answers, which I'll define in a second, on more than half of the weight of the distribution on queries. So what does that mean? It means that the probability, if you sample from this distribution on queries, that you get a good answer. Good is going to mean for us that the value that we get when we apply the query to the object is within lambda of the value, the true value of the query on the database. So we want that probability to be more than, by a constant fraction, half of the weight of this distribution. So the probability, if I choose according to that distribution, of getting a good answer should be more than a half plus eta. Okay? So later, I will wave my hands and say a tiny bit about where the base learner comes from. But it turns out you already know that too. So for now, let's just assume that we have a base learner that does this, and let's look at our boosting algorithm. So you've seen something like this before, only now we're starting with a uniform distribution on the queries. Each query has weight 1 over the size of Q. And we sample from that distribution. We feed the samples into the base learner. It produces an object A that will do well on at least a half plus eta of the weight of the distribution. Yes?
Label means you know the answer, the true answer.
Oh, I'm sorry. Just get rid of the word labeled. I mean, it's just, I shouldn't have had that there. My apologies. All right. But I like you're right, we will use the true answers. So in that sense, that would be a good use of the word labeled. Thank you. Yeah. Okay, so it produces an object that's going to do well on a half plus eta of D. And, you know, at some point, we're going to have stacked up A1 up to whatever. We're going to combine them. We're going to check whether we're going to check whether to terminate. The way we're going to check whether to terminate. If we do, then our combiner will be our median, the median of the outputs, because we're going to have real valued outputs now, and we're just going to take their median. It's a well-defined notion. And if we don't terminate, and I'll tell you the termination condition in a minute, then we're going to update, and that's going to involve this +1 and -1 in the exponents like I gave on the previous example. Oh. My termination condition, I'm not sure where it is in the slides. My termination is we're going to run this algorithm for a fixed number of rounds. That fixed number of rounds will end up having a form that you know and recognize by now. So deciding whether or not to terminate is trivial, and it's certainly not private. Everybody knows how. Ooh, this is offline. Anyway, just deciding whether or not to terminate, there's nothing interesting there. It's going to go for a fixed number of rounds.
So, just to understand, there's now a distribution of queries, so it's just kind of average case?
No, it's not going to be an average case analysis, but I'm going to I am going to learn an object, or I'm going to learn an object that is good for answering lots of queries for this database. No, my query set is fixed in advance. This is an offline algorithm. It's an offline algorithm, and I'm going to run boosting on the queries. Okay? It's an offline. Okay.
Setup is different in the sense here the privacy is instead of announcing just an answer to a query for you added knowledge.
Right.
Now you're going to announce this database.
That's right. As I said, my goal is to produce some kind of an object. Maybe a synthetic database, maybe a data structure, I don't know. Maybe it's a little algorithm. But it's going to have the property that once I announce it to the public world, for every query in the set, it's going to produce it's going to allow somebody to produce a good approximation to the value of the query on the database.
Which you do by boosting, but now you have to show us privacy.
Right, right. But what's surprising here is that the boosting is being done on the queries. Okay, so, right. So the question now is privacy, as Ravi said. Where are there privacy worries for us? The privacy is for the people in my database. I'm constructing this object O. Where, and what I want to do is I want to run an algorithm that's composed of a bunch of differentially private pieces that I will then put together with a composition theorem. Where are the privacy risks? I mean, you know more or less how the algorithm works. I told you. So this, and the sampling, and so on. Where are the privacy risks? Why is an unasked query a privacy risk? My privacy is for the guys in the database. I'm not worried. The query set is public. Everybody knows what the questions are. In fact, they were the input to the algorithm. So where are the privacy risks?
So the only place where we are asking the database is from baseline to this.
So say that again. You're in good shape. Go on.
The only place where we ask, querying the original database is on that step.
Which one? This one?
Yeah.
In the base learner?
Yeah, we are putting up some queries and we are saying that more than half of them.
Okay. But remember, I assumed I had a private base learner that when given a small set of samples produced something that would do well on a half plus eta of the distribution. So I already took care of that with the assumed private base learner. Yeah, very good. So that's one place, the samples that are being fed to the base learner. These are sample queries. Okay, so what's going on? Yes, there's the issue with the base learner, but we handled that. There's the renormalization step. How the queries get renormalized depends a lot on who's in the database, because it depends on which things were answered well. Which things were answered well might depend on who's in the database. That will affect the sampling that's done in the first step. And the whole issue here, the reason things are really tricky, is that a single individual can affect the answers of very many queries. Okay? So my presence or absence doesn't just affect how one query gets reweighted. It might affect how all of them get reweighted. And so my presence or absence affecting how everything gets reweighted then affects the sampling that's done at the top. That affects what's getting sent to the base learner and so on. So this is really our struggle. Again, privacy is problematic because in boosting for queries, an individual can affect the quality, Q of AT, simultaneously for many Q. So what happens, the worry, is that as time progresses, the distributions, D sub T, that we get on neighboring databases could start to evolve completely differently. And so that distribution just looks wildly different on neighboring databases. That will affect what gets fed into the base learner. That in turn will affect the hypotheses that are generated because the base learner is working with different samples. So we have to keep the distribution secret, and we can make our lives a little bit better. I mean, our lives are inherently a little bit better because we're dealing with sampling. If we don't have to feed in too many samples, that will help things a little bit. But it's still problematic. So that's our struggle. So again, reweighting, we want to be similar under x and x prime. You should need a lot of samples from D in order to detect the difference. And we're going to try to arrange that the adversary never gets its hands on many samples. That was a lot of work. So the key is going to be very simple. We're going to call it attenuated reweighting. So until now, I had said that reweighting was, if this query was unhappy, boost it by adding 1 to the exponent. If the query was happy, meaning the current hypothesis gave a good estimate, then lower it, right? And those are pretty big changes. So we want to smooth that out. So instead of saying, if the query is well approximated, decreased by a factor of, is well approximated, decreased by a factor of E, we're going to say if it's very well approximated. So we're going to have some slack. If it's very poorly approximated, then we'll increase. And in between, we'll scale. Instead of doing a plus or minus 1 to the exponent, we're going to choose some number between plus and minus 1 in a very natural way. We're going to choose a parameter u, and we'll talk about the choice of u later, but it'll be kind of chunky. And what we're going to do is we're going to scale with the distance of the midpoint between, so this is the error here. Things where the error is less than lambda, those are good. Things where the answer is more, the error is more than lambda plus mu, that's going to be bad. And in between, so these are going to be, this is going to be the plus 1 guys, these are going to be the minus 1s, and for everybody else, we're going to scale with the distance to the midpoint of this interval. So the distance to the midpoint divided by this chunky factor, which I haven't told you yet, called mu. So this chunky factor is going to take something which is kind of high sensitivity, and it's going to scale it down. One person's presence or absence won't affect what happens to this particular query Q by 1. It's going to affect it by at most 2 times the sensitivity divided by mu. Okay? So I'm scaling it down. Let's go back to this in a minute. Right, sorry, that should be last. My animation. Wait, you can't see what's going on. Sorry. So remember, this is the form of our algorithm. In each round, we're taking K samples. We're going to run the base generator to get a synopsis. For every Q, we're going to run the attenuated reweighting, which I just described, and that'll give us a new distribution. And our output is the median. So let's think about, oh, can't see it very well. Let's think about what the privacy loss is per sample. Well, we saw that. We showed that for every sampled query, the sensitivity was 2 times rho divided by mu. Mu is our attenuating factor that we put in there. Okay? So let's just say that that's on the order of 1 over mu. We're going to treat each sample as a kind of differentially private mini-mechanism. And we're going to use composition to show that in each round, given that we have fixed the history, the total privacy loss is going to be on the order of k to the 1/2. K is the number of samples. This is where we're using composition. K to the 1/2 divided by mu, because the sensitivity for any one is 1 over mu, and I've got k of them, and I get to use that square root of k from the composition theorem, rather than k times it, plus k over mu squared. That also comes from the composition theorem. Okay? So the total privacy loss in this particular round will look like k to the 1/2 divided by mu. And we'll choose things so that k to the 1/2 over mu and k over mu squared are about the same. Now, it will turn out that for an accurate base sanitizer, we need something like, we need to feed about n samples. I'm just telling you that this is true. And in order to, but if our error is as big as n to the 1/2, that will give us privacy. So if the So we're going to feed to the base sanitizer k queries. We're going to get something which on those queries is going to be accurate to within n to the 1/2, and in fact on many queries is going to be accurate to within n to the 1/2, which is good enough to give us privacy, and it's non-trivial accuracy, because the maximum error could be n. So this number is so small that we could even afford to increase this by a small polynomial, like n to the 1/6. And that will allow us to control the cumulative privacy loss over all t rounds of our algorithm by increasing mu just a little bit. So the algorithm, the theorem that you end up with is that we choose mu to be, well, how many rounds are we going to have to run this thing? By arguments similar to the argument that I didn't tell you for the multiplicative weights update previously. It's the same kind of argument. It's going to be log of the size of q divided by eta squared. And then we have to throw, so this is how many rounds we have. I forget why we square it. We're going to throw in square root of k because we have k samples per round. And this is the thing that we divide by with, of course, our epsilon. So the only thing I didn't tell you is how to get the base learner. And the base learners come from previous work. If you were only handling counting queries, then it turns out that if I feed about on the order of n queries, I can take n queries, I can compute their answers, and there's a little tiny database. Oh, where did you hear about these little tiny databases before for counting queries? From the Blum-Liggett and Roth result. So there's a small database that will answer the selected queries well. Then there's an argument that says because this is small, it actually has what's called good generalization error, which means that we chose these queries at random, we produced something that answered these queries well, but because it's somehow very compact, we haven't overfitted too much, and it's actually going to do well on most of the queries, or on a big chunk of the queries. So that's what happens here. For arbitrary real-valued things, we do less well. We're going to do the same kind of thing. We're going to choose these about n arbitrary queries. We're going to fit an n-element database to it. We know there's at least one because the original database is that good. But we fit an n-element database to it. And we're going to get bounds that are less satisfying. Still interesting, but less satisfying. And the reason for the difference is related to the size of the AlphaNet that you need for handling arbitrary query sets versus counting query sets. You saw the AlphaNets before in the Blum-Liggett and Roth. That was for counting queries. And your AlphaNet has to be bigger for arbitrary queries. Okay. So that is what I prepared for this morning. So we went over the sparse vectors, where we had these k queries, this large number of queries, but not too many of them were above threshold. We only paid a privacy price for the ones above threshold. Then we used that for private multiplicative weights that let us answer lots and lots of counting queries with pretty good accuracy. And that introduced the sort of the idea of boosting, but it was being done on universe elements. Then we switched to arbitrary queries, went offline, but used boosting again, this time for the queries. Okay, very ambitious day.